The first topic that confuses students is acceleration. Imagine you photograph an object at position x1 at time t1. A moment later, it is at position x2 at time t2. What direction is the acceleration? This is a trick question, as there is not enough information to answer it. You need a third photograph of the object. Let's say you observe it at position x3 at time t3, such that it has covered more ground in the same time interval. Doing the vector math, you take velocity v2 and subtract velocity vector v1, and you will find v2 minus v1 is pointing to the right. So in this case, acceleration is in the direction of motion. However, if the third photograph reveals the object has covered less ground in the same time interval, even though the two velocity vectors are to the right, the difference in velocity is to the left. v2 minus v1 points in the direction opposite of motion. In this case, acceleration is to the left, even though the object is moving in the positive x direction, and the acceleration is negative. The object here is slowing down or decelerating. You can find the third photograph may reveal the object has turned around and the velocity vector goes from the positive direction to the negative direction. The change in velocity v2 minus v1 points to the left. Although the velocity momentarily is zero, the acceleration across these three photographs is a non-zero number. The key takeaway is acceleration is not necessarily in the same direction as the motion. If an object is moving in a circular path with constant speed, the change in velocity, shown by taking vector v2 and subtracting v1, reveals the direction of acceleration is towards the center of motion. This is called centripetal or center-seeking acceleration. Now, not only do you know the direction of the acceleration, but by pure geometry, you know the value of the acceleration, which is the square of the speed divided by the radius. This is very useful for objects moving in circular motion. Now that we have clarified the concept of acceleration, let's say you are given a problem of something moving in a straight line with constant acceleration. Write down these 5 parameters: acceleration, displacement, initial velocity, final velocity, and time. In all cases, you must be given 3 parameters to solve for the other 2 unknowns. Using the definition of acceleration and the definition of velocity, a couple of other equations can be derived which are used frequently. Keep these equations handy when solving linear motion problems. Let's do an example. You drop an apple from rest. How far does it drop after 2 seconds? How fast is it going? Let's write down the 5 parameters and figure out what we know. We know the time interval is 2 seconds. What else was given? Dropping from rest means the initial velocity is 0. Okay, we need a third piece of information. The assumption is we are on the surface of the Earth, so the acceleration due to gravity is 9.8 meters per second squared downward, which I've rounded off to 10. You'll notice I wrote down a positive number for the acceleration. I'm going to treat down as positive. However we define the coordinate system, the results will be consistent with the system we define. If I chose up was positive and the acceleration was negative 10 meters per second squared, then the resulting velocity and distance will be negative. Let's use the equation, which is the displacement is equal to v naught t plus 1/2 at squared. We plug in what we know, and we find that the apple has fallen 20 meters in that 2 seconds. Using the definition of acceleration, we find out that the velocity is 20 meters per second. Now I want you to think about what we would have found if the time was 1 second. We would have calculated a velocity of 10 meters per second and a distance of 5 meters. You should realize that the velocity is increasing 10 meters per second every second, and that the displacement is going by the square of the time. For a two-dimensional motion, such as tracking trajectories of projectiles, write down the 5 parameters in each direction. The same methodology applies as in the one-dimensional problems. Given 3 parameters, you can find the other 2 in that direction. Then time is common in both directions. Let's do an example. A ball is thrown at 5 meters per second at an angle of 45 degrees to a level ground. How far does it go and when does it land? We will write our 5 parameters in each direction. So what do we know? We know the initial velocity, but it's only the component in each direction that counts. We also know the displacement in the y direction is 0 because the ground is level. We assume we are on the Earth's surface, so the acceleration in the y direction is 9.8 meters per second squared down, which I've rounded off to 10 meters per second squared. Just as important is realizing the acceleration in the x direction is 0. The concept is to separate the two-dimensional problem into 2 separate linear motion problems, analyzing the shadow of the ball along the ground, which moves with constant speed, and the shadow cast against a vertical brick wall. The motion of the ball in the y direction is identical to if you simply threw the ball vertically upwards and it came back down. You'll notice we know 3 parameters in the y direction, so let's solve for the time for the shadow on the brick wall to return to its original position. The equation selected produces 2 answers. Both are physically meaningful. A time of 0 is produced as a solution because that is when the ball crosses the x-axis when it is first thrown. The second solution of 0.7 seconds represents when the ball lands. This time can then be copied over to the x direction, and we now know the 3 parameters in the x direction, allowing us to solve for the distance of 7 meters. Moving on to forces, Newton's second law of motion says the sum of the forces acting on an object equals the object's mass times its resulting acceleration. The acceleration and force are vectors, so you can add the forces graphically, and the resulting net force dictates the acceleration. Newton's second law is valid in each direction, so the common way of approaching a multidimensional problem is to break down the forces into components in each direction and solving interrelated one-dimensional problems. Newton's first law is simply a special case of the second law, where the net force is 0. The resulting acceleration is 0, so the velocity is constant. A body at rest stays at rest, and a body in motion stays in motion. Newton's third law is that every action has an equal and opposite reaction. If you push on a wall with a force of 10 newtons, the wall pushes back on you with the same 10 newtons. When analyzing forces, it is useful to draw a free body diagram that depicts all the forces acting on a mass. Determine if the body is accelerating or in static equilibrium. The surface is modeled by a normal force perpendicular to the surface and a friction force parallel to the surface. Cables or strings can be represented by tension forces, and springs can be expressed by Hooke's law. Write Newton's second law in each direction, knowing if you can set the acceleration to 0 in either direction. A force that exists in virtually every problem is gravity. If you have 2 masses separated by a distance r, according to Isaac Newton, they will attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. The capital G is the proportionality constant and is a fantastically small number. If you draw a free body diagram of mass m1 and write Newton's second law, you find its mass cancels out and its acceleration is dependent on the other mass m2 divided by r squared. If you repeat the process for mass m2 and calculate its acceleration, once again you find out its own mass cancels out. The takeaway here is although the force is dependent on an object's mass, its acceleration in a gravitational field does not depend on its own mass, as demonstrated by Galileo when he dropped two objects from atop the Leaning Tower of Pisa. Let's consider a planet orbiting the Sun. We draw a free body diagram of the planet and apply Newton's second law, just like before. This time, we approximate the motion of the planet to be moving in a circular path, so we can set the acceleration to the velocity squared divided by the radius. Once again, the mass cancels out. Now, astronomers didn't know a planet's velocity, but they could measure the time for it to go around the Sun, so it's more convenient to express the velocity as the circumference of the circular path divided by the orbital period. The resulting relationship between the square of the period and the cube of the radius is Kepler's third law. Measuring the parallax between planets gave the distance to the Sun, and knowing the orbital periods, you can calculate the mass of the Sun. In fact, this is how the mass of the Sun was determined before we knew the mass of the Earth. Weight is the gravitational force acting on an object by a planet. Even though your mass is the same on different planets, the force pulling you down is different, so your weight is different on other planets. As seen in previous slides, the acceleration of a mass in free fall near the surface of the Earth is a constant depending on the mass of the Earth, not the mass of the object. When you do the math, you find this acceleration is equal to 9.8 meters per second squared, which we assign the lowercase letter g. If the object is supported by a surface, like the ground or a table, a normal force counteracts the weight and it's no longer in free fall. In fact, the acceleration is zero. The takeaway is that you can simply assign an object's weight as equal to mg in most free body diagrams. Buoyancy is an upward force due to a body's displacement of fluid surrounding it. Buoyancy can be seen when liquid is displaced, like when a cork rises upwards in a fish tank, and also when water vapor rises in the air, which is why clouds are in the sky. Water vapor is less dense than air. Drawing a free body diagram and writing Newton's second law describes how the buoyant force opposes gravity. If a mass is completely submerged in a fluid, Archimedes' principle states that the volume of the fluid displaced by an object equals the volume of the object. That's how you can measure the volume of a body, is dunk it in water and measure how much spills out. The other tip for these buoyancy problems is expressing the mass in terms of density times volume. So how do we quantify the buoyant force? Well, if you were diving in the ocean, your weight would pull you down. If you were made entirely of the fluid, you would be in static equilibrium, so the buoyant force would be equal to your weight. So the buoyant force is equal to the weight of the fluid displaced by your volume. You can write Newton's second law and calculate your acceleration if submerged, or the density ratio if floating. Just remember, the buoyancy force is equal to the weight of the fluid displaced. For motion down an inclined ramp, first draw a free body diagram including the weight and surface forces and tilt the coordinate system so that the x-axis goes down the ramp and the y-axis is normal to it. This results in the acceleration being zero in the y direction. The angle between the weight vector and the normal vector equals the angle of the ramp. Many people get tripped up on the components of the weight vector. It's the sine, not the cosine, of the weight vector that points down the ramp. This is because the sine component is opposite the angle and the cosine component is adjacent to the angle. Write Newton's second law for each direction. In virtually all of these problems, you will be given enough information to solve two equations for two unknowns. Get comfortable solving two equations, so expect to use algebra to solve for one unknown and then substituting it back into the other equation. It's common to solve the second equation for the normal force and plugging that into the first equation. A lot of times the mass cancels out, but it starts with Newton's second law in x and y directions, and remembering the adjacent component to the angle has the cosine, which may be in the y-axis rather than the x-axis. Consider a block with mass m attached to a spring with stiffness k. You pull the block to the right in the positive x direction and let go. Drawing a free body diagram shows that if the block is displaced to the right, a force from the spring pulls the block to the left. If we set the equilibrium point when the spring is relaxed to x equals 0, Hooke's law states the force is equal to kx. Writing Newton's second law, we see that minus kx is equal to ma. If you started taking calculus, you can write the equation with derivatives, but even if you don't recognize the differential equation shown here, the important thing to realize is that the acceleration is negatively proportional to displacement. The solution to this equation is a sinusoidal function. By convention, because we want the full displacement to coincide with t0, we will express the position as a cosine curve, oscillating with an amplitude a. The Greek letter omega represents the angular frequency and is the square root of the spring stiffness divided by the mass. This parameter is important when studying vibration and is related to an object's natural frequency. The velocity is a negative sine curve. Notice how the velocity is initially 0 and then increases to the left. The acceleration is a negative cosine curve, meaning that the pull is greatest at the extreme and goes to 0 when the spring is relaxed. As the velocity reaches its maximum value of a omega, it starts to get pushed to the right by the spring and it starts to slow down. In other words, accelerating to the right. The key takeaway for simple harmonic motion is that there is a restoring force that ensures acceleration is negatively proportional to displacement. Waves are energy transported by a propagating disturbance, where each constituent moves in simple harmonic motion. Consider many masses suspended by vertical springs and connected in a way that motion of one mass affects the mass next to it. In this example, each mass vibrates with sinusoidal motion in the vertical y direction with an amplitude a slightly out of phase with each other, resulting in a sinusoidal wave developing in the x direction. Whether it's fans watching a game in a stadium or a cork bobbing in the water, the constituents do not move entirely along with the wave. They oscillate around an equilibrium position. In addition to the angular frequency omega, a wave number k also appears in the equation. This is a different k constant than the spring stiffness. Both k and omega scale 2 pi radians to a cycle, one over distance and the other over time. One full cycle in distance is the wavelength, and one full cycle in time is the period, capital T. The velocity and the acceleration of the masses are also sinusoidal functions, just like simple harmonic motion. The velocity of the wave, which moves at constant speed, is frequency times the wavelength. This example shows masses of a transverse wave because the particle motion is perpendicular to the wave direction. A longitudinal wave, such as sound, has air molecules vibrating in the same direction as the wave. Light is a transverse wave, but there is no mass that vibrates. Rather, it consists of oscillating electric and magnetic fields. The key takeaway for waves is to distinguish between the motion of the wave, which is moving with constant speed, versus the sinusoidal motion of whatever is oscillating. Momentum is mass times velocity. Much like force, momentum is a vector, but instead of acceleration, it's the velocity that dictates the direction of momentum. Momentum is useful because if there is no external force, momentum is conserved. This is because the center of mass of a system doesn't move if there is no force. For physics problems analyzing collisions, write out the conservation of momentum and don't forget, if it's a two-dimensional problem, momentum is conserved in both directions. If there is an external force on the system, Newton's second law can be rewritten to determine the change in momentum. The expression on the left, a force applied over a certain time, is called impulse. It's common to see a graph of force versus time of an impulse and be asked to determine the change in momentum, which is the area under the curve. Oh, by the way, light waves have momentum even though they have no mass. That's a trick question since Einstein related energy and mass. The key takeaway is if there's a problem about collisions, write out the conservation of momentum for all directions. Consider an object spinning, carving out an angle theta over a time interval. Each parameter we learned in linear motion has an angular counterpart. Angular velocity is denoted by Greek letter omega, and angular acceleration by Greek letter alpha. All those linear motion equations we covered earlier have an angular version. Remember how if we know 3 parameters, we can solve for the other 2. The same principle applies to angular motion. Mass and force have equivalent terms for rotating objects. Rotational mass is called the moment of inertia I and describes how mass is distributed around an axis of rotation. The average radius that gives the equivalent resistance to motion, as if all the mass were located there, is called the radius of gyration. A force that causes rotation is called a torque. Newton's second law and momentum have angular versions. You can see the conservation of angular momentum in play when a figure skater brings her arms inward while spinning. As the moment of inertia decreases, the angular velocity increases, keeping the angular momentum constant. Let's talk about work, energy, and power. Work is defined as the displacement of an object times the force in that direction. Mathematically, that's called a dot product. Remember, the force and displacement must be parallel for work to be done. How much work does gravity do on a crate you push across a frozen lake? 0. How much work does gravity do on a car sliding down an icy hill? Not 0. It's the car's weight times the vertical height of the hill. No displacement means no work regardless of the force. The work-energy principle says that the work equals the change in energy of a system. Work and energy are measured in Newton meters or joules. Energy comes in different forms. If an object is moving, it has kinetic energy 1/2 mv squared. If there is stored energy, it is called potential energy. Raising an object stores gravitational potential energy mgh. Stretching a spring stores potential energy 1/2 kx squared. The conservation of energy can be used to quantify how energy is transferred. Energy can be dissipated as heat by non-conservative forces such as friction. Without friction, energy remains constant, and if you have friction, the mechanical energy loss equals the work done by friction. Power is work or energy per unit time and has the unit of watts. Let's do an example. You drop a 10 kilogram mass from 3 meters and it lands on a spring with stiffness 50 newtons per meter. What is the velocity when it impacts the spring, and how far does the spring compress? The key concept is realizing the total mechanical energy remains constant through the process. There is no friction in this problem to worry about. Over the 3 snapshots, or states, you find that certain terms equal 0. For example, initially there is 0 kinetic energy or spring potential energy. So the energy is simply the gravitational potential energy, mgh, in this case 300 joules. Right before the block hits the spring at state 2, there is only kinetic energy, and setting 1/2 mv squared equal to 300 joules gives a velocity of 7.7 meters per second. By the way, you'll notice you get the exact same answer if you worked out the velocity as if it were a linear motion problem. However, you need to calculate the energy to find out the compression of the spring. This is a great example because you use the quadratic equation and get 2 answers, both of which have significance. One solution is positive, the other is negative. The spring compresses 6 meters, but if the box sticks to the spring, guess what happens? The block moves in simple harmonic motion 2 meters above its equilibrium position, which is 2 meters below where it started thanks to its weight. In other words, the block vibrates with an amplitude of 4 meters around a position of 2 meters. The entire time, the total energy remains the same. For bonus points, you could calculate the natural frequency of oscillation. While two masses attract each other with a gravitational force, there is another force between particles that have electric charge Q separated by a distance r. Coulomb's law quantifies this electric force to be the product of the charges divided by the distance between them squared. Charges can be positive or negative, so the force can be attractive or repulsive. Like charges repel and opposite charges attract. The unit of charge is called a coulomb, and although atomic particles have tiny charges, the proportionality constant of the electric force is 20 orders of magnitude stronger than gravity. When an electric charge Q moves with velocity v, a magnetic force is created equal to the charge times the velocity times the magnetic field strength. Charge times velocity equals electric current times length. The magnetic force is perpendicular to both the velocity and the magnetic field in accordance with the right-hand rule. Stick your fingers out in the direction of the magnetic field lines going from north to south. Your thumb points in the direction of the current, and your palm is the direction of the force on a positively charged particle. In 1865, James Clerk Maxwell published 4 equations unifying electric and magnetic fields. Changing electric fields creates magnetic fields, and changing magnetic fields create electric fields. He realized an alternating electric field would produce a self-propagating wave. This electromagnetic wave is radiation, which includes visible light, ultraviolet, infrared, radio waves, and X-rays. He calculated the speed of the wave was based on 2 universal constants, the permeability and permittivity of a vacuum. This concludes this video of your first year of physics compressed into a half hour. Hopefully this video improved your understanding and provided some tips. I've listed some key developments where classical physics theories have been updated, replaced, and modernized. The world is non-static, non-continuous, and non-deterministic.